module, we consider the relative comparison of two competitive tests through asymptotic methods. Actually, if the two tests are consistent, then we cannot use the exact results that are available in the literature, and when we use fixed alternative, we cannot use such results. The regularity conditions are numbered by A1, A2, A3, etc. First regularity condition, suppose theta naught belongs to omega naught and theta belongs to omega A are such that theta greater than theta naught. Then we take theta n is equal to theta naught plus b by root n, where b is positive, so that theta n belongs to omega n for all n and theta n tends to theta naught belonging to omega naught as n tends to infinity. Suppose there exists mu function of theta under Tn and sigma function of theta under Tn positive, and this is positive, such that under theta naught Tn minus mu theta naught under Tn divided by sigma theta naught under Tn, that goes to the some distribution of W, and under theta n Tn minus mu theta n of Tn divided by sigma theta n of Tn converges to the sum distribution same as W, where W has some known continuous distribution with distribution function HW is equal to probability that W less than is equal to small w. In particular, W can be taken as normal 0, 1 distribution. Now assumption 3, first derivative of mu Tn theta with respect to theta exists and is non-zero and is continuous in the neighborhood of theta naught. Assumption A4, there exists a positive constant d such that 1 by root n into mu prime Tn theta naught divided by sigma Tn theta naught is equal to d, with mu prime Tn theta naught is equal to derivative of mu Tn theta with respect to theta at theta is equal to theta naught. And assumption 5, limit n tending towards infinity sigma Tn of theta n and divided by sigma Tn of theta naught is equal to 1. Next we get a result. Under the above assumptions, the asymptotic power AP of a test is probability that W greater than small w alpha minus Bd, where W alpha is such that probability measure of W greater than W alpha is equal to alpha. Proof of this result. Since phi n is asymptotically size alpha, we get alpha is equal to limit n tending towards infinity, that probability under theta naught of Tn greater than Cn, which after some manipulation gives the using the assumption A1 probability that W greater than W alpha, and where W alpha is such that W alpha is equal to 1 minus alpha. Thus we get Cn minus mu Tn theta naught divided by sigma Tn theta naught tending towards W alpha as n tends to infinity. Now AP of phi n against theta n is given by AP is equal to limit n tending towards infinity, probability that Tn greater than Cn under theta n is same as that probability of Tn minus mu Tn theta n by sigma Tn theta n greater than Cn minus mu Tn theta n divided by sigma Tn theta n under theta n. And since Cn minus mu Tn theta n divided by sigma Tn theta n after some algebraic manipulation goes to W alpha minus Bd as n tends to infinity using assumptions A3 to A5 and A1 and the equation star, we have AP is equal to probability that W greater than W alpha minus Bd, and hence the proof is complete. It is worth to mention that this AP belongs to alpha 1 open interval. Now we consider the testing problem H naught theta belongs to omega naught against H A that theta belongs to omega A for getting asymptotic relative efficiency and its definition. Suppose we have two tests phi n1 based on T1n and phi n2 based on T2n. Both the tests are assumed to be right-tailed and asymptotically size alpha. Let kn and k prime n be two sequence of positive integers such that both kn and k prime n are increasing in n, and as n tends to infinity, kn and k prime n tends to infinity. Again, these sequences are such that power of the test under theta n of phi 1 n and the power of the test of phi 2 n are both lying in the open interval alpha 1. Then area of phi n1 relative to phi n2 is defined by area of 1 relative to 2 is limit n tending towards infinity k prime n divided by kn, provided the limit exists and is independent of the sequences kn and k prime n satisfying the requirement given above. Thus, area is the limit of the ratio of the sample sizes required to reach the same limiting power against the identical sequence of alternatives for tests with respect to the same limiting significance levels. The area is equal to 2 means that we need approximately twice as many observations for test 2 as compared to test 1 to reach the same limiting power for the same sequence of alternatives. Naturally, test 1 is better or worse than test 2 in the limit according to area is greater or less than 1. Next, we come to the determination of asymptotic relative efficiency. However, the definition of area as given above is not enough to compare in practice. Thus, we need some equivalent expression so that the efficiency can be evaluated easily. The following result gives an equivalent expression of area. If the test phi n1 and phi n2 satisfy the regularity conditions as given earlier, the regularity conditions are given in the form of A1 up to A5. Then area of the test 1 relative to 2 is defined by limit n tending towards infinity of 1 by root n of mu prime T1n theta n divided by sigma Tn theta naught whole square divided by limit n tending towards infinity 1 by root n mu Tn prime theta naught divided by mu sigma Tn of theta naught whole square. From the definition of sequences kn and k prime n, we have probability that T1 kn greater than C1 kn under theta n and probability that T2 k prime n greater than C2 k prime n probability under theta n, that two probability has the same limit as n tending towards infinity. Since phi n1 and phi n2 satisfy the regularity conditions A1 to A5, these two limits are nothing but their APs. For example, the limit of probability under theta n of T1 kn greater than C1 kn is the asymptotic power of phi n1. Then we have from result 1 that limit of p theta n of T1 kn greater than C1 kn is equal to probability that W greater than W alpha minus BD1. Similarly, phi n2 we get the expression of AP as probability that W greater than W alpha minus BD2. Thus, we require Kn and K prime n to satisfy that the limits of the two are equal. That means we have limit after some simplification. limit n tending towards infinity k prime n divided by kn is equal to the required result as given in the statement of the result 2. This completes the proof. Next we get a remark. From the expression of ARE, we observe that under the regularity conditions, the ARE can be interpreted as the ratio of two efficacy measures where the efficacy of the test based on Tn is defined as limit n tending towards infinity of 1 by root n mu Tn prime theta naught divided by sigma Tn of theta naught whole square. Next we get a remark. The expression of ARE remains valid even if the alternative is two-sided. The ARE does not depend on alpha and beta so long as the regularity conditions are satisfied. Thus, unlike fixed sample efficacy, the ARE does not suffer the disadvantages. Now we get some examples. We consider some testing problems. Suppose xi, I from 1 to n are IID observations from fx minus theta, where theta is the location parameter, and fx plus f of minus x is equal to 1. That means the distribution function is symmetric about 0 when theta is equal to 0. Consider the testing of theta is equal to 0 against the alternative theta greater than 0. Now, for this testing problem, we have three types of tests. One is based on T1n is equal to root over n x bar by Sn, which rejects the null hypothesis that theta is equal to 0 against theta greater than 0 when T1 is greater than C1n, where n minus 1 Sn square is equal to summation xi minus x bar whole square, and x bar is the sample mean. And we have another test which is called sign test. The test statistic is defined by T2n is equal to 1 by n summation I xi greater than 0, where I is the indicator function, and the test rejects H naught against HA if T2n is greater than C2n. Next we get test 3, which is Wilcoxon signed rank test, and that is based on the statistic T3n is equal to summation I less than 0 j of capital I xi by xi plus xj divided by 2 greater than 0 divided by nc2, which rejects the null hypothesis if T3n greater than C3n. Now consider the sequence of local alternatives theta n is equal to b by root n, and assume that variance of the distribution function is finite. First of all, we verify the condition A2 to A5. Since Sn converges to sigma in probability, root over n x bar by Sn and root over n x bar by sigma have the same asymptotic distribution. Thus, this suggests to define mu T1 n theta is equal to root n theta by sigma, and sigma T1 n theta is equal to 1. Then condition A3 to A5 are all satisfied with D1 is equal to sigma to the power minus 1. Now, by applying central limit theorem, we get T1 n minus mu T1 n theta sigma Tn theta converges to normal 0 1 in distribution under both theta is equal to 0 and theta is equal to theta n. Thus, A2 is also satisfied. Hence, the efficacy of the test 1 is ET1n after some computations is sigma to the power minus 2. Next, considering sign test statistics, we find that T2n minus f theta divided by root over f theta into 1 minus f theta divided by n converges to normal 0 1 in distribution by de Moivre Laplace limit theorem under both theta is equal to 0 and theta is equal to theta n. And next, defining mu T2n theta is equal to f theta and sigma T2n theta is equal to f theta into 1 minus theta by n under root, we can satisfy the conditions A2 to A5, and these are all satisfied with D2 is equal to twice of small f0, where fx is equal to dfx by dx exists at all x and continuous with f0 greater than 0. Hence, the efficacy of the test 2 is defined by 4 f0 square and at 0. And finally, we can compare different pairs of tests using ARE. First of all, consider comparison of sign test with respect to t-test statistics. The ARE is given by 4 sigma square into f square 0. Naturally, ARE depends on the underlying density f. Thus, we provide below the expressions corresponding to different distributions. The table below gives the results for some specific distributions. For example, when fx is equal to normal 0, 1, ARE gives 2 by pi, that is equal to 0.64. Similarly, for logistic 0, 1 distribution, we get ARE is equal to 0.82. For double exponential distribution, it is 2.0. For rectangular -1 to +1 distribution, it is 0.33. For Cauchy 0, 1 distribution, it is infinity. Thus, we observe that the sign test is always less efficient than the t-statistic based test, except for double exponential distribution. Roughly speaking, for normal parents, we would require 36% less observations for t-test compared to sign test to get the same performance. This is not unexpected, as the sign test uses only the information about the signs of the differences. However, for heavy tail distribution like double exponential, the quality of information used by the sign test is improved and hence becomes twice as efficient as the test based on t-statistics. This shows that t-statistic based test is no longer desired for double exponential distribution. For information, we note that within the class of all continuous unimodal symmetric densities, ARE of sign test relative to t cannot be lower than 1/3. For this, one can consult the book by Hodges and Lohmann for details. From the above table, we find that only the distribution attaining the lower bound is rectangular -1 to +1 distribution. Next, considering Wilcoxon sign rank test and the test based on t-statistic, we have ARE of sign rank test relative to t is 12 sigma square into integral f square x dx whole square. As before, we can also obtain a table for different density functions, and these are given in the form of table 2 comparing sign test relative to test based on t. And finally, we can obtain ARE of sign test relative to sign rank test, and this is also given in the form of a table as given earlier. We have shown that asymptotic power of each test under fixed alternative is unity. So, we are not able to compare those tests, and to compare those tests we have used sequence of local alternatives for which the asymptotic powers belong to the open interval 0, 1. In fact, it lies between alpha and 1, and finally we compare those tests from those asymptotic results.